Okay, so prove the product of three consecutive odd numbers is odd. So let me just write this out quite formally. So let's write down the consecutive odds, right? Now you can go 2n plus 5, but I'm going to go 2n minus 1, right, the number before. And notice I've already made one error because it's now the product. So we're going to look for the key words. Can you see I've done some? So let's just go ahead and erase that. So I dive straight in, right, for the sum, because that was previously all of the questions. And what we've got to do is we've got to prove that this can be written as 2k plus 1. Okay, that's what we've got to prove. Notice I was being quite technical here. The three little lines for identity, right, identical, as opposed to an equation to solve to get solutions. Really, all of these proofs should really have the three lines here for identity, identical to. I suppose it's okay if we lapse out and have an equation sign here. They're almost interchangeable, but this technically is the correct symbol to have. Remember, odd over here, and z, the family of integers. Remember z for Zahlen from the German, to add up. And z is closed under these operations, right? So if we take an integer and add or multiply or subtract another integer, we will always get an integer. That's what closure means. And also if you have a positive integer power, right? Integer to the power of a positive integer would give you also an integer, right? I'm thinking, 3 cubed 2 to the power of 7, but of course not a negative integer and certainly not a fractional exponent. Okay, so with all that in mind, let's go and dive into the proof. The reason why I chose this little guy down here is that you should recognize the difference of two squares here. All right, so this will be 4n squared minus 1. So that maybe speeds up the multiplication a little bit. And I'm going to tell the reader I'm working on the left-hand side. And eventually I want to try and prove that that can be written as a 2k plus 1. So let's go ahead and expand now. That's 8n cubed plus 12n squared minus 2n and then minus 3. Now we want that to be in this form, 2 times something. I can see a small problem, but there's a little cheat basically. There's a top tip here. We're going to change that negative 3 at the end into negative 4 plus 1. And maybe now you can see it, because what we're going to do is we're going to factor out a 2 from here, and then we're going to leave that plus 1 at the end. So we're always looking to have a plus 1 at the end to shape it. So even if we've got a negative number here, we can always turn it into something plus 1 at the end, right? And now the final step is here, 2 4n cubed plus 6n squared minus n minus 2 plus 1, which does indeed equal to 2k plus 1, which is equal to the right hand side. And I suppose really if we want to be formal, we do that. And one final thing is the old Latin used to have QED, and I think, if my Latin serves me right, quadratus demonstratum, that which was meant to be demonstrated, right? We wanted to demonstrate or prove this statement, and we've certainly got it. I think in the 50s or 60s, I'm not very good at my dates, I think a Hungarian mathematician, Paul Erdos, decided that that was too old-fashioned, and he puts a nice little filled-in black square at the end of any proof, so that's what we'll do as well. So there we go, we've proved it. I suppose on the side, you could decide to put where k is equal to the substitution you used. You don't really need to do this, but for completeness. And then we'll just check, well, look, can we see that this is a integer cubed, and that will create an integer squared, right? And then any multiplications and additions and subtractions of integers, because z is closed under all these operations, we are definitely convinced and certain that this expression is indeed an integer. So there we go.